Okay, welcome everyone. Thank you for coming to this version of the Young-HOM seminar. Today we have our very own Julie Rasmusen, co-organizer of this seminar, talking to us about an overview of the theory of enriched infinity categories.
Thank you very much. I'm going to be talking about the general different approaches there are to enriched infinity categories and why these different approaches makes sense. There's been several different ways people have been trying to do it in the last couple of years, both by Gepner-Haugseng, Hinich, and Heine have combined it, but there still isn't any uniform language that has been used. So many people see enriched infinity categories as unnecessarily scary. So I hope to help people a bit see that it's not as weird as it might seem. So first of all, let's try and understand what kind of structure it is that we want. So if we start with just a one category, a monoidal category V, then a V enriched category. Let's call it C, consists first of all of a set of objects, just call it up C. And then for any pair of objects, we need a HOM object, which is an object just denoted C, X, Y, that needs to be in the category we're enriching in. Furthermore, we need some composition maps between these HOM objects. So from C, X, Y, tensor C, Y, Z into C, X, Z. And we need unit maps. So for each object X, we need a map from the unit to C of XX. And we need this composition to be associative and unital. And some of the key examples that are relatively easy to understand is that if we enrich in the category of sets, we just get locally small categories. If we consider chain complexes, we get DG categories. And if we enriched in category, like the category of categories, we get strict two categories. And then the one that people here probably think most about is if we enrich in simplicial sets or topological spaces, then we get infinity one categories. But the thing is, this is a lot of hands-on structure. So the question is, how do we generalize this? Because the thing is, when we work with infinity categories, we really don't want to have to spell out the structures. Like we get a little bit of an issue with an infinite amount of data. So how do we generalize this? And the answer is through an alternative way of looking at enriched categories, namely through multi-categories. This one is not as intuitive, but it's easier to generalize. So multi-categories, which is also known as non-symmetric colored operand, can be thought of as categories with morphisms having a list of objects as the source. So a multi-category M consists again of a set of objects, noted object M, and then for a string of objects x1 to xn and y in M, we need a set denoted by M and then x1 up to xn into y, which is a set of multimorphisms. That goes from the string of objects x0, xn into y. And then again, we also need an identity multimorphism. It just goes from the one string object into x. It must be, yeah. And then the associative and unital composition laws again. Okay. And between these, as with other kind of categories, we also have functors, and this works exactly as one would assume. So a multifunctor f from m to n between two multi-categories just assigns the object object-wise. So it takes just one object x and sends it to f of x. And if we have a morphism, it just takes and apply f to each entrance in the string of this in the source. So it just goes to f of x1, string up to f of xn, into f of y. In a way, again, that's compatible with unit and composition. And one of like the key and easiest examples is if we have a monoidal category, we already have an easy way of getting a multi-category, denoted by the tensor, where we just define the set of multimorphisms to be the normal set of maps from x1 tensor up to xn and then into y. So we can use the monoidal structure to consider this as a multi-category. And the way we'll need to look at it is through algebras. So an algebra of a multi-category M in a monoidal category V is a multifunctor that goes from the multi-category into the monoidal category considered as a multi-category. And it's a specific form of algebra we will care about. So we need a specific multi-category. So if we have a set S, we can define a multi-category OS to have as objects just the set times the set. And then the weird thing is in the multimorphism set. So if we have this string here, so each object is a pair of objects in S. So we have x0, y1, x1, y2, and then all these goes into y0, xn. And we want that to be exactly one map if yi is the same as xi for I between 0 and n, and then empty otherwise. And this might seem a bit arbitrary, but if we start to consider algebras in like OS algebras, for example, let's note this by C, so it goes from OS into V, considered as a multi-category, it gives us the kind of structure that we're interested in. So first of all, if we have two objects, should write it like this, okay, the x and y, then we get an object C, x, y in V, just because that's how a functor works. And then we have a unique map that goes from the empty string over the case n equals 0 into x, which will give us a unit map. So that will go from ix into C of xx. And then similar, we have a unique multimorphism that will go from xy, yz into xz, which when we then apply C to this, we get a composition, which we can write as C of xy tensor cyz into cxz. And then by looking at triples of pairs, we can get that this is associative and unital, and we can write out all the structure that we need. So what this gives us is that OS algebras in V is the same as a V-enriched category. C with space of objects being S. And the thing is that this approach, considering OS algebras, we can generalize. And the way we do that is by thinking of enriched categories as many object associative algebras. And if we want to consider, like, if we want to make an infinity categorical version of associative algebras with many objects, then there is two ways we can do it, right? When we are considering the algebra, we can either do something and get an operatic gadget in the source that takes care of all of the these many objects or in the target. And there's 2 projects that's been doing this. There's by Gepner-Haugseng, where it is in the source that they consider an operatic gadget that takes care of all of this coherence structure. And then there's an approach by Hinich, which changes the target. So it's an associative algebra that goes into quivers x of v. And the one I will be talking about these 2, so these have been proven to be equivalent. The most well-known and used is the one by Gepner-Haugseng. Yeah, so I will be focusing on that one. Also, it's a lot easier to see where we get the structure that we want when we're considering that. Yes. So our first attempt at understanding enriched infinity categories will be by considering them as many-object associative algebras. And for that, we need an infinity categorical replacement for the non-symmetric infinity for the multi-categories, which is the non-symmetric infinity operands. And they're very similar to what you're probably used to of infinity operands, with the main difference being that instead of considering things over pointed finite sets, it's over delta up. So a non-symmetric infinity operand is an inner vibration laying over delta up, such that for any inert that we have, and from M to N, and any object in the fiber over N, there exists a pi co-Cartesian morphism x to phi of x laying over our map phi. Furthermore, we want that for any object N, we have a functor that goes from the fiber over N into the product of the fiber over 1 times N, induced by the co-Cartesian arrows from the inert, like the standard inerts maps. And we want this to be an equivalence. And then there's some more conditions on the mapping spaces that does not necessarily give that much intuition, but makes annoying proofs work, basically. Okay, so as you can see, it's very much similar to what we're used to about infinity operands. Yes. And what we will really care about is morphisms of these non-symmetric infinity operands. So a morphism between 2 non-symmetric infinity operands O and P here, where we have, like, as part of the structure, we have a map down to delta up. And such a morphism will then be a commutative diagram like this, which takes and preserves the co-Cartesian lips of inerts. So if we have a co-Cartesian lip here that lays over an inert, we want that to be mapped to a co-Cartesian lip as well. This is also called an O algebra, which leads us to define the subcategory of the functors from O to P laying over delta up that preserve these co-Cartesian lips, and denote this by O algebras in P. And by using categorical patterns, we can take these non-symmetric infinity operands and their morphisms and gather them into an infinity category. Okay. The thing is that we can go from multi-categories to non-symmetric infinity operands in a relatively nice way. So the idea is we have a multi-category, and then we want the nerve of a version of our multi-category to be a non-symmetric infinity operand. And I'm probably gonna not write the nerve, but it's in theory there. So if we have a multi-category M, we can define the category of operands denoted by M and then a little tensor, to have, first of all, as objects, just lists of objects from M, so x1 to xn, and then a morphism between 2 such lists consists first of all of a map in delta phi that goes from M to N. So here worth noting that the N is the last part here, and M is what we go up to here. And then for each j between 1 and M, we want a multimorphism in M that goes from a string of objects of x's that are determined by this phi, and then into yj. And the thing is that if we consider the category of operats on our multi-category M, then an object, right, is just this string. So we have a very logical map from this category down to delta up, where we just send this to M. And this can be shown to be a non-symmetric infinity operat. So the logical way to try and consider enriched categories and generalize our earlier approach is by considering the multi-category OS from before. So if we have a monoidal category V and some set S, then we can define a V-enriched category with a set of objects S to be an OS algebra in V. So it's a morphism of these non-symmetric infinity operats. And this does give the desired structure. So if we have like an object xy in OS, then we get an object c xy in V, and then the map x from the pairs xy, yz into xz, laying over the map d1 from 2 to 1, will induce a map from C applied to like the entire string, but this will be equivalent to C xy tensored with C of yz into C of xz. So we get our composition map. And similarly, we also have a lift of S0 that will go from, again, the empty string into XX in this OS category, which will give us our unit maps. But as you might have noticed, there is one problem with this. Like, we get the structure that we're interested in, yeah, but we're not quite happy because we don't want a set of objects. We want a space of objects. And the way that is fixed in the one categorical version is by considering virtual double categories instead of multi-categories. And just very hand way, like a virtual double category consists of objects, vertical and horizontal morphisms, and then cells with lists of vertical arrows as a source. And what this gives for us will be is that the fiber over 0 does not need to be trivial. So this can be non-trivial. And we want the fiber over n to be equivalent to the fiber over 1, fall back over fiber over 0, 1. So we want a Siegel-Resk type condition. And instead of going through the one categorical case here, let's just jump directly to what it is in our case. And it is what's called generalized non-symmetric infinity operats. And the idea is simply to generalize the non-symmetric infinity operats so the fiber over 0 is not necessarily contractible. And the key thing to doing this is that as part of our definition for the non-symmetric infinity operats, we had these lifts that we considered that were induced over the standard inert maps. We want to consider the co-Cartesian lift of the inert map n to 0 and the standard inert map from n to 1. So a generalized non-symmetric infinity operad is again an inner vibration from some category O laying over delta up. And the first condition is the same as in the previous case. So given a map from M to an inert map from M to N and an object in the fiber over N, there needs to exist a co-Cartesian morphism or lift of it. The change comes in part 2. So before we had that, we considered the map from ON to the infill product of O1, and we wanted that to be an equivalence, and that was induced by the co-Cartesian lift of the standard inerts. Now what we consider is map from ON into the limit taken over the map that goes from N to I, where I is either 0 or 1, and these need to be inerts, and then taking it of OI. And this can be shown to be equivalent to what we were interested in, namely O1 over O0 times O0, O1. And yeah, this is then induced by the co-Cartesian arrows over the inert maps, the standard inert maps, and the ones from N to 0. And we want this to be an equivalence. And we just define morphisms in the same way as before. So a morphism of generalized non-symmetric infinity operads from O to P is again a commutative diagram such that co-Cartesian lifts of inerts are mapped to co-Cartesians. And we call these again also O algebras. And we can turn these into category of O algebras to P. And using categorical patterns, these can also be formed into one big category. That's denoted by OPNS, GN for non-symmetric generalized infinity operand. So the story is very much the same. So in this case, so I think I forgot to mention that when we are considering general non-symmetric infinity operads, if the operad is also co-Cartesian, we call it a monoidal category. Again, just as we do in the symmetric case. But when we're looking at generalized non-symmetric infinity operads, we call these double infinity categories. If the infinity operad is, again, co-Cartesian. So this is like the double infinity category is the generalized version of a monoidal category. And there is a reason for the name. Like if we have a double infinity category O to delta up, then because it's co-Cartesian, we can apply straightening to obtain a simplicial category C dot that will go from delta up into cat infinity, which will satisfy Siegel-Rest condition. So Cn will be equivalent to C1 over C0 times C0, C1, which is exactly the internal categories in the infinity category of infinity categories. So the name is not completely arbitrary. Okay, and as we did in the one categorical case, it is specific kind of algebras that will give us the desired structure. So we need to construct this category, or like this operatic gadget that can keep track of all of the coherence for us. And the way we do that is that we fix a space X, and then we consider this diagram here. So we have a functor that goes from the category with one object, 0, and we send that to X in spaces. And then we have the inclusion down to delta up, and we can then take the right can extension of this diagram. And what this right can extension will do, in objects at least, is they will take n and it will send it to a list of n+1 objects in X. So it will map it to X0, Xn, which will be in X times n+1. Yes, and we can then straighten this map to get a functor where we denote the source. So we get a co-Cartesian map, a source that goes from what we denote by delta up x down to delta up. And what it will do is exactly like, because we know what the right can extension do, we know that through unstraightening here, that it will have strings of objects of x0 to xn laying over n. So it is this kind of many objects operatic gadget that we're interested in. And then if we have a monoidal category V, so that is a non-symmetric infinity operator that is also co-Cartesian, we define a categorical V algebra with space of objects x to be a delta up x algebra in V. And I will come back to why it has this name later. There is a reason for it and why this is not what we want as our V-enriched categories. But let's first see why this, again, gives us the kind of structure that we're interested in. So if we let C go from delta up x into V, so we let this be a categorical V algebra with space of objects x. Then again, if we have a pair of objects, x, y, then that is sent to C of x, y, and v. And if we have a triple, so x, y, z, that will lay over 2. So the map D1 from 2 to 1 will induce a map from x, y, z into x, z in delta up x, and then when we are applying C to this, we get our composition map as we would want it. So C of xy times C of yz into C of xz. So we get the composition maps. And similar, if we have an object x in x, then the map from 0 to 1 induces the desired map from x to x point x in delta up x, and then when we apply C to it, what lies over V over 0 is just the monoidal unit. So we get a map from the monoidal unit into C of x. And like the key example of this to understand why this works, like we can see here, we get the correct structure, and we can continue looking at longer triples to get all of, like, see we have the correct coherence data that we want. But the reason that this actually can be thought of as many object associative algebras is because an associative V algebra is the same as a categorical V algebra, which has a contractible space of objects. So as a key example is that for a monoidal category V, we can consider its monoidal unit as a V-enriched category, or a categorical V algebra with just one object. So it will go from delta up, then just a point, into V, and it will just take the point and send it to the monoidal unit. But okay, so we have, like, we can see here that by considering this delta up x, we get the correct kind of information that we're interested in. So now we would like to turn this into a category, so we can start considering like the collections of these. The way we do that is by first noting that the way we constructed this delta up x was functorial in x. So we can consider this as a functor from S up from spaces into generalized non-symmetric infinity operators, and then we can apply like the algebras from blank into a fixed monoidal category. And then we can take the unstraightening, one or the other, to obtain a category that we denote by alk cat V to S, which is the associated Cartesian vibration. And the thing is, in the fiber over a space X, we will exactly have the categorical V algebras with space of object X laying in that. And it's a result that if we consider the categorical algebras in spaces, this is equivalent to Siegel spaces. But this is where the problem arises. What we want is that if something is enriched in spaces, we would want that to be equivalent to infinity categories. So we need some sort of completeness condition. So we can use that the complete Siegel spaces are infinity categories. And there is a way to construct this hands-on and then show the result that I'm going to mention in a second. But because I mainly personally care about the categorical algebras, that's what I mainly actually look at. And we can see all the structure that we're interested in there. I won't go into so many details about the specific way of defining this completeness condition. But what I do want to say is that it's a result that the category of infinity categories is equivalent to the category of categorical S algebras localized at a suitable version of fully faithful, essentially surjective enriched functors. So therefore, it makes sense, like using this approach, seeing this, it makes sense to define the enriched categories as objects in the category denoted by cat V infinity, which is the categorical V algebras localized at the fully faithful, essentially surjective functors. So that's a way to look at it, to go this way about it. Okay, so this is a setup where we can see that we have all of the necessary data that we're interested in, and it's a relatively nice, straightforward way to look at it because it follows our intuition from normal higher algebra. But there's also another approach that I would like to talk a bit about, which maybe is a bit more geometric. And that is to consider enrichment through a so-called closed action. So as motivation, just that V be a closed monoidal category, then if we have a V-enriched category C, which has so-called V tensors, then the V tensors endows C with a closed V action, or actually a left closed V action. And then on the other hand, if we start with a category with a closed V action, then it has an underlying V-enriched category. Which admits V tensors. And this enrichment is induced by the assumption that the V action is closed. So that means that V-enriched categories with V tensors is the same as a category with closed V action. So the idea is that we want to consider V-enriched categories as a relaxed version of categories with this closed V action, in which these V tensors does not need to exist. Because here, as it is right now, if we just consider closed V action, then we're getting more structure than we actually need. We don't necessarily want these V tensors. So we want to relax the assumptions. And as I mentioned, this structure is in theory left actions. I will be focusing on the right tensored version because that is what connects, first of all, to the other approach where we consider it as many object associative algebras. Okay, so we start by some definitions. So we denote by BM the category delta up sliced over 1, so morphisms from n into 1. And we just note that objects in BM we can consider as a string of objects of the form 0, 0, 1, 1. And we can then define Rm to be the subcategory of BM consisting of those tuples of the form that either only have 1, 0, or no zeros at all. And there are canonical projections from both BM and Rm to delta up, and these canonical structures makes both of these into double infinity categories. That means that if we're starting with a generalized non-symmetric infinity upright M, we can define B mods by modules on M to be the BM algebras in M, and similarly for R mod on M, that is the Rm algebras on M. Okay. And if we consider the inclusion of delta up and then just like the one set object with 1 into delta up, then by composing with this, we get a projection from the right modules on M down to the algebras from delta up to M, and we can take the fiber of this map at some algebra A, and we obtain the right A modules on M. And the reason I just wanted to spell this out is to say that the way we're looking at like the right modules and bimodules here agrees with Lurie's definition, even though we are using another starting point for our operands. Okay, so using that we have Rm as a double infinity category, we can define this right tensor thing. So a weakly right tensored infinity category is a morphism of generalized non-symmetric infinity operands, which we denote now by Q, that will go from some M into Rm, such that both M0, so the fiber over 0, and the fiber over 1 are contractible. What we do is that we denote by M the fiber of M over 0, 1, and MR tensor, the generalized non-symmetric infinity operand we obtain by applying this projection map I to our map M, so by pulling that back. And in this case, what we say is that Q exhibits the fiber over 0, 1, so MM, as weakly right tensored over MR. And again, we like it when our maps are co-Cartesian. So here, if Q is furthermore co-Cartesian, we call this right tensoring closed. No, not we just say it's right tensored. It's not weakly right tensored, just right tensored. And like one key example that we would want to be tensored over itself, because we're starting with a tensor, is if we have a monoidal category. Then we can consider the pullback along the map from Rm to delta up down to Rm, and this will exhibit the fiber over 1 as right tensored over V. So it works as we would want. Like we can use the tensor from monoidal structure to also get right that it's right tensored. So that is good. Okay, and the intuition of why this gives us the a right tensor structure is if we start with Q exhibiting some C as right tensored over category B, then through unstraightening we obtain a functor that F that will go from Rm into cat infinity, such that when we apply it to 0, 1, it will be equivalent to the category C. And if we pull back along that projection map I, then that corresponds to the associative algebra, is the associative algebra corresponding to B. So that means that we can consider this functor F as being Rm monoidal in cat infinity, which is the same as right modules on cat infinity. So therefore, we can think of this Q map as giving rise to an action map, or some weak form of tensor that goes from C times V into V, which will be well defined up to homotopy and compatible with the monoidal structure on our category B. So it does have this form of tensoring. Okay. Next what it means is that we need this, we had that this action was closed. And we can also extend that to this setting. So if we assume that Q from M to Rm exhibits C as weakly right tensored, that is none. Weakly right tensored over some category B, then if we have an object V in B and two objects C0 and C1 in C, we write map C and then C0 box V into C1 to be the category of maps in M that goes from the pair C0 V into C, which is mapped to the unique active map from 1 to 2 in delta. And we say that a right morphism object of two objects in C consists of, first of all, an object, which we'll denote by FR C0 C1 in V, and a morphism that goes from C0 box FR, and then this morphism object C0 C1 into C1, such that when we're composing with that, we get an equivalence between maps in V from a little object B and then the morphism object, and then into this weird box thing we had. So C0 box B, C1. Want this to be an equivalence for all B. And we say that Q is closed right tensored if there exists a right morphism object for all pairs in C0, C1. So what we're basically assuming here, or forcing on it, is that we need there to be some sort of HOM tensor adjunction, but where it's not actually a tensor and it's not necessarily really HOM. It's these morphism objects instead. Okay. And we can continue this and define it to be a category. So the category of closed right tensored category is the full subcategory of like maps from generalized non-symmetric infinity operas to Rm, which satisfies these conditions. And by using the inclusion from delta up into Rm, we obtain a projection from closed R-tensored categories into monoidal categories. We call that pi. And we denote by R-tens the L of V, the fiber of this map at V. So that consists of all of those maps from something M to Rm, where we have a category that is tensored over V. And a way to look at this is that if we have a map Q from M to Rm that exhibits C as closed right tensored over monoidal category V, then that is equivalent to saying that for every object C in C, the right tensoring functor, C think blank, I'll go from V to C, admits a right adjoint, which will be the morphism object. And the thing is, everything we just did with Rm could dually have been done for Ln. So Lm is the full subcategory of Bm of the strings of the form that either have just one or no ones in it. And so that we can get a dual theory of left tensored. And the main difference that one will see is the composition of the morphism objects. So Fr, AB, tensored with Fr, BC, int goes into Fr, AC. And this is directly compatible with our composition of the categorical V algebras, which is why I was focusing on the right version. But on the other hand, if we had considered the left version from the beginning, then we would have left morphism objects, which compose differently. So and this is more compatible and is the way with the way that things are done in, for example, higher algebra. So a lot of it is up to conventions and how you prefer to look at it. But there is a nice connection between these. So if we have a monoidal category, we can consider, so it's a category V tensor down to delta up, and we can compose that with the opposite functor that takes a set and then reverses the structure. That will again be a monoidal category. We denote that by V rev because the structure is reversed. And we can also, from delta up, this opposite functor, we can extend to Bm, which will then take and send Lm to Rm, and vice versa. And this induces an equivalence between closed left tensored categories on V reverse and right tensored categories, closed tensored categories on V, which will take a category C up and send it to C, as one would assume. Then as a comparison between these two is that it's a result by Heine that if we have a monoidal category, then closed left tensored categories and V reverse, which we recall was the same as R tensored closed on V, is the categorical V enriched categories that we saw earlier. And you see I'm about to run out of time, so I'll just state this proposition and that be it. So yeah, is there a question? Okay, so just as the last result, is that there exists a functor that goes from stable infinity categories and exact functors into spectrally enriched infinity categories, which preserves the underlying infinity category. And I won't go through the proof, but just mention that the interesting thing here is that it needs both versions of looking at these different enriched categories. So the final thing I want to say is a little overview of why one would use one over the other. So the many-object associative algebras it's easy to see that we get the correct structure. And it follows our higher algebra intuition, which I personally find nice. And it packages up all of the structure really nicely for us. Like, we don't have to worry about keeping track by things by hand. So well packaged. But the fact that it is so nicely packaged also makes it's also a negative thing. It makes it very, very hard to work with. And as a result of that, it wasn't possible to using this structure to prove a unit lemma. And you know, as a category theorist, life is really hard if you don't have a unita. But then on the other hand, we have the closed tensor categories. And it might be harder to see that you get the right information, but it has more of a geometric intuition, which for some people is a big plus. And it is not as nicely packaged. You have all of the structure still out there, which is more hands-on, so it's easier to actually work with sometimes. But that is also a problem because nothing is really keeping track of all of your structure for you, so you can end up with a lot of bookkeeping. But because this is more hands-on, this is the setting where it has been possible to prove a unit lemma. And a final positive of the many-object associative algebra approach is that it is the easy way to extend to something I like to call enriched algebra, which I won't go into details about. Okay, I think that was it. Thank you very much for listening.